Hello and welcome to Super Simple Scala episode 7. Today we will try to brute force our way through a lot of the features. Um, I'll be using this little repository, John Reed Lowell Understanding Scala. If you would like to follow along in IntelliJ, you can open a new project, file new project from version control, GitHub, provide the repository URL, clone it, set your version of Java, Scala, then go to run, edit configurations, add a configuration for Scala build tool, file new SVT task. We couldn't call it like run SVT, and that just handles your run for you. Apply. Okay. And we'll be using that. Really quickly, we'll start with variables. For AA equals 1, val AA equals 2. Second one is final. It's an immutable reference. If you've ever taken C++, it's like a constant pointer. This is a variable. You can modify it. So you can say, AA1, let's call this AA2. You can say like val AA3, let's say BB. You can modify, you can say something like, AA equals 6 or 7. That's legal. But if you try to say something like AA1 equals 7, that's illegal because it is immutable. So that's that. Let's go back to there. All right. These little curly braces represent a scope. A scope will return the very last thing in the scope. In this case, the last thing is left string plus right 1, which will be string 1. So we can call this a scope. This is an import. We're just importing a method from my library that will provide a position. If you look under here, when I click on it, it goes to that line just for convenience. So you can see that this is printing string 1. These functions accept string 2, and accept string 3 are 3 different kinds of functions. If we go to their declaration up top, Control B, we'll see that this just takes in a regular string, a reference to a string. This takes in a reference to a function 0, where a function 0 is an object that takes in 0 parameters and returns a string. Assigning it will cause the result to have a type of nothing arrow string, so a type of a function that returns a string, whereas calling its apply method, .apply, or just parentheses causes it to execute, returning the string. If you go back down to here, you'll see that you actually created a new function 0 of type string. So this here creates an anonymous inner class. You override the apply method, and it'll return string 2, which is why here we have string 2, because the result of calling accept string, result 2, this is going to be equal to what we passed in, which is string 2. Accept string 3 is a scope that represents something that returns a string. This is confusing to some people. Colon arrow just means anything, a block that returns a string. So this block could be a value, or this block could be a function, but it's just something that returns a string. Internally, this will get converted into like a function 0 like this, so that when you actually do this assignment, it's actually going to actually execute the code that's associated with the block, and it's going to assign the result of that code to result. So we go down to accept string 3. You can think of this whole block here as like a block of code that upon assignment is executed. And when the assignment occurs, it'll print in, hey, we are getting string 3. So hey, we are getting string 3. And this hey, we're getting string 3 is executed on the assignment, because this is kind of like, you can think of this as like a function. If we were to do this twice, so val result equals s, and then val result, let's say result 2 equals s2, what would end up happening equals s again, and we were to execute this, what would end up happening is that there's a bug. Let's just run it with SPT instead. Sorry for the delay, but what's going to end up happening is that the code that we put into that curly braces block is going to be executed twice. So if we looked at here it is. So hey, we're getting string 3 is going to, so this block here is executed 2 times because the assignment happens twice. This is a standard function declaration. If a function, it used to be possible to just do, well, no, it is possible just to leave out the equal sign often. Not here because this is being inferred, but you'll see here this still. If you leave out the equal sign, it'll return unit. So unit is like the nothing type. It's like void in Java. But it's usually a bad idea to leave out the return type and leave out the equals for a couple of reasons. The equals is going to end up being mandatory in a future version of the Scala compiler. Also, specifying the return type aids in type inference. It prevents unexpected return types from being inferred. It slightly reduces compilation time, and sometimes it's necessary for recursion. Recursion sometimes doesn't work if you can't infer the return type. Here we have initialization with new, just like in Java. Control B goes to declaration. We can assign this value to something. In this case, we're assigning it to 2. Or we can use a method, in this case the apply method of the array object, to instantiate. This is going to create an array with 1, 2, 3 in it. If you press Control B on apply, you'll see that there's this apply method, takes in 1 int and then a var arg. The star means var arg, variable number of arguments. If you've ever used C, it's the same kind of idea as var arg in C or other languages. If we read this code, it says you have a new array of type inth where the length equals the var arg's length plus 1. The first element is the first element that's being passed in. For I equals, so this is mutable, I equals 1. For x is x2. So this is an iterator for XS iterator. This iterates over the entire length of this var arg container. And then we're saying array at I, and in this case like array at 1, array at 2, array at 3 equals the iterator. So we initialize this empty array, and then we're assigning each of the elements in the empty array from the varg, and then we're returning that empty array. So apply for objects is often used for, so this array here is actually an object. So the difference between classes and objects is that an object has just static stuff. So in Java, you used to like mix together the static stuff with the stuff that belonged to the instance of the class, and you would have the static keyword. Scala doesn't have the static keyword, so all the static stuff is put inside of objects, where the name of the object is the same as the name of the class. So in this case, we have an object or an array, and we would also have a class array, where the class array has the variables that belong to each instance, and the object array might have like static methods that generate a new array, like apply. Oftentimes, we'll call the object that has the same name as the class the companion object, and so each class has a companion object. The apply here is if you were to either do .apply or just that, they're the same thing. If you're curious about the syntactic sugar, it's so confusing, what's going on, you can compile it with, if you go to build.spt, you can compile it with -xprint typer, or compile it with -xprint parser, and you'll get these partial compilations. So here's a partial, like a intermediary compilation phase. if we look at our intermediary compilation phase, we'll see some stuff, right? So we have our main object. We'll see extends anyref. Anyref is the superclass of all references in Scala. There's also anyval, which is a superclass of all non-reference values, like like int and float, double, long, and then the superclass of all those is any, a and y. We've got the initializer for our main object. It's not a class because there's only one instance. We notice that the semicolons are being inserted by the compiler, so there's a semicolon here. There's no semicolon of the last thing, so you would end up with something like, assignment, and then boom, this last thing is returned. You'll see occasionally, instead of so here we have root.scala.function0 string. Root is the very base of the tree of directories, the tree of packages. Sometimes when you give the name of a package, it's relative to the current directory. So like if you say like package like slash something, sometimes you mean slash something from your current directory, and sometimes you mean slash something from the base directory. And so this underscore root makes it perfectly clear that we're referring. I'm back. Sorry. So root is our sort of the base of all the directories. This is after the phase 1, the parser compilation phase. If you are interested in the compilation phases in Scala, you should Google something like Scala remove syntactic sugar stack overflow, and second one, and it'll show you like maybe halfway down. It'll show you all the different compilation phases. This answer right here, answer number 7, very good answer. What it's doing is it's showing you this command line option, -xprint parser, that will show you the output of the different compilation phases. So you can do -xprint parser, xprint namer, typer, etc., and it'll show you what your code will compile into. So here we see string func.apply, semicolon, and just string func with the braces. We see that plus is actually turned into $plus. We'll see some other things. That's phase 1. If we were to go to phase 4, the compilation phase 4, the typer phase, and look at it, we have even more syntactic sugar removed in this phase. So we are going to end up seeing something like, see how here this is string func.apply, and that's also string func.apply. Well, what it means is that, and here it's .apply and then just parentheses. So what ended up happening was in between phase 1 and phase 4, this dot, that ended up turning into that. And if you're interested, you can go through the compilation phases and see, what transformations happen at what phase. I'm going to actually stick to the parser phase just because this is sort of desugared, but it's not like indecipherable. So we have accept string 1, val string 2. We created this anonymous inner class, anon, that extends function 0 of type string, which is the same as new function 0 of type string. We just didn't give it, we didn't give an explicit name, anon. Although if we really wanted to, we could. Accept string 2, accept string 3. Here we see that accept string 3, we actually end up with these curly braces are getting inserted underneath the parentheses. The difference in between the parentheses and the curly braces oftentimes is, so if we just had, let's say, curly brace and curly brace, right? Oops. My bad, not here. Wrong place. I meant, let's just undo some stuff. Right. I messed up something. I know I did. Anyway, here. So except string 3, and then we have parentheses curly brace. And then if we go to parser 1, we would have parentheses curly brace. So those end up being the same. But if we were to get rid of the curly brace, something bad is going to happen. It's going to be like, type mismatch, accepted string, actual unit, whatever. Because curly braces are only supposed to accept, not curly braces, sorry, the parentheses are only supposed to accept a single line. So if you were to get rid of this part, it would compile because this is only a single line, right? So that's a single line. That's perfectly fine. As soon as you want to make it multiple lines, you need to add in those curly braces. And because it's really, really ugly to have parentheses, curly brace, you can just get rid of these extra parentheses just for the aesthetics. Or if you want to be like explicit and be like, yo, I want to be like more detailed or whatever, you could, whatever. Or just to be really anal, let's say you left in the no, even if you leave in the semicolon, it still doesn't like to have multiple lines with a parentheses. You still need the curly braces. This is how you define a function. If we were to go and see the exact same function, the typer phase, we would see that this plus actually gets converted into dot plus parentheses. So what ends up happening is this ends up being the same as that, right? Oh, it's possible to leave out the curly braces for a single line. So this is actually the same as that. Sort of the same way you would, do that with like if statements or whatever, but I don't know, I like leaving them in just in case you need to add more stuff there later. This is called a type alias. You're basically assigning int type to int t, and then wherever you used to be able to use int. So for example, you could say, val3 of type int equals 1 plus 2, and you'd be like, 3 is 1 plus 2, and that's an int. You could use int t there and be the same thing, or you can let the compiler infer the type. And if you press Control Q in IntelliJ, it'll tell you pattern 3 is of type int. I end up using Control Q a lot just because you end up using it for something like you end up using Control Q for pulling up documentation in your IDE, and you also end up using Control Q to show you what the type of something is. And since it's not like Java where the type is explicitly told everywhere, sometimes you have to use Control Q to get one or two types, then you can kind of figure out what all the other types are from there. Oftentimes, one of the hardest sort of things for people in Scala is the type inference system. I just press Control Q on stuff and look at what the types of those things are, and then try to mentally prove what the other types are from there. Sort of like, if you press Control Q, it tells you it's an int. This int goes into a function that takes in an int and returns a string. Oh, what comes out has to be a string, and then that string gets passed somewhere else. And you kind of look at it like, step 1, this type goes in, that type goes out. Step 2, the type that just went out now goes in. Third type comes in, and you can kind of derive how the types go from there. That's the best advice I can give about that. There are existential types, which are, you can think of them almost like, don't know types. We don't know what this type is, but let's just, play it safe. Existential types will, we'll see later. But there are two ways to write existential types. You can say, define a function called accept existential that takes a sequence of whatever type for some type whose name is whatever. We can also put bounds on it. So we could say for some type whose name is whatever that is a subtype of any. We don't actually need to say subtype of any because everything is a subtype of any in Scala. Or any ref, or any subtype of int, and maybe you want to say something like subtype of int, super type of nothing. Oops, I got these backwards. Sorry. Let's do like super type of nothing and subtype of any. Yeah. So this means super type. That means subtype. If you're wondering why isn't if super type is an arrow that's like this, why isn't subtype an arrow that goes in the reverse direction? So why don't you just flip the arrow? And I think what Martin Odersky was thinking when he was doing the symbols is that colons bind to the right. So if you had like a function that was like val list 1 equals 1 : nil, that would be the same as val list 1 I'll call the same equals nil dot : 1. So the colons bind to the right. So what I think Martin Odersky was thinking when he thought of these symbols was, hey, if the colons bind to the right, then the colons are going to stay in place, and the only thing that's going to switch sides is the thing that's to the left of the colon. So here we're saying, the colon binds to the right, and we're saying, okay, so here the colon binds to the right, and we're saying the inheritance goes like in that direction, where any is like, parent type goes down, where whatever type is a subtype of any, so the arrow goes down. And then here, to flip the arrow over, we're keeping the colon in place, and then we're just flipping the thing that's not bound. So then this means supertype. So what we're saying here is type whatever is a supertype of nothing and a subtype of any. Nothing is the very bottom of the type hierarchy. Everything is a supertype of nothing. Any is the very top of the type hierarchy. Everything is a subtype of any. So by default, everything is a supertype of nothing and a subtype of any. That doesn't actually, this is sort of like automatic here, right? If we were to change this any to like any ref, and we were to change this nothing to int, now we have like an actual, more sensible range. Why is this not compiling? Oh, you can't actually. Yeah, you can't use int there. But with existential types, you can set the default lower bound is nothing, the default upper bound is any, but you can set the lower bound and upper bound to whatever you want them to be, and the compiler will try to do whatever is safe, assuming that the type could be any type that fits within, that's higher than the lower bound or lower than the higher bound. So let's go back to nothing and any, just because that's like the default. And then there's another way of saying it, except essential sequence of just underscore, just fill in the blank, right? Where you could say, fill in the blank is a superclass of nothing, a subclass of any, just like that. There we go. Yeah, so these mean the same thing. It's good, if you have an idea of what the existential type could be, it's good to specify a higher lower bound or a lower higher bound, because then the compiler can sort of safely guess types to fill in the blank. The type that we don't know what it is, the blank. So for example, if we so we have these two, which are the exact same thing, and then we have one that just takes a sequence of int. And let's create a sequence of type whatever. Let's cast it, make the reference type of sequence underscore, where this sequence underscore is the same as underscore that is a super type of nothing and a subtype of any. So this, it could be some type. We don't know what it is, but we can guess sort of what the bounds are. And we're creating a list of int, and we're going to assign it to this reference. we can pass this into there, into either existential 1 and existential 2, because it fits into the bounds. And then, but we could also sort of change the bounds and things will change. Keep in mind that these arrows mean, the top bound is inclusive. So if it goes up to any, it can include any. And if it's down to nothing, it also can include nothing. So whenever we pass an existential into a method, into a function, we don't know what the type is, but we want to, pass in what ends up being sort of the lowest type possible, just to be safe. So, for example, if we passed in something like accept int sequence of whatever type 2. So we have this, it's an existential type, sequence of underscore. We don't know what the type is. We actually don't need this to be listed twice, but whatever. When we actually go to accept ints, we're expecting an int, but we're passing in, we don't know what the type is, sequence of something that we don't know. We just know that it has to be, it has to be equal to or higher than nothing, and equal to and lower than any. So it could be an int. We could be like, oh, if it's an int, it'll totally not throw an exception when we try to call it, right? But it also could not be an int. And because there's that possibility of it not being int, we have to play it safe and say it's nothing. It's the very bottom of the type hierarchy. Whereas if we return it, we don't know what the return type is, but we want to be as, with the return type, if we're returning an existential type, we want to be as vague as possible because we don't know what it is. So when we're returning it, it goes to the type sort of defaults to sort of the furthest on the upper bound, whereas when we're passing it in, it defaults to the furthest on the lower bound. And the lower you make the upper bound, the higher you make the lower bound, the more sort of places that it'll work, because the more types, the more places, functions that you could pass it into. But yeah, for the time being, it's just like a generic that has its own unique little bounds on it, and each little generic can, so it has its own unique upper bound, it has its own unique lower bound, and you don't know what the type is. So it's like almost like you can think of it as if you've ever seen like a void pointer in C or C++, a pointer to something where you don't know what the type is. It's like a void pointer that has an upper bound and a lower bound. Sort of, I guess, the way I think of it. So passing an existential int doesn't work because it might not be an int. In Scala, names can be symbols, so you can have a name like symbols equal of symbol, like the name could be that, and we'll be like, oh my god, that thing is an int, right? What is going on here? There we go. Well, what's going on here is that, well, first off, you'll actually, if you have you have to have a white space between all these symbols and the colon, otherwise it thinks that like the colon is part of the symbols. But it thinks, so this thing is actually a variable name. Functions can have symbol names, methods, variables can have symbol names. Usually you avoid symbol names unless the symbol is something like super recognizable, like, plus symbol or equal symbol or something like that. If you want to have ASCII characters, alphanumeric characters, as well as symbols, you have to separate that with a colon. I'm actually curious if you could also have multiple colons. No, you get one colon. But yeah. Control Z, go back to undo. Traits, these are like interfaces, but they can also have data in them. This is saying that there, in this trait, there's a type, my type, that is a subclass of motion. And if we, create a subclass of that trait, we can also sort of override my type and give it any type that extends motion. So we can think of, we're almost like treating types as if they're values here. There are different scopes: private this, protected this, private motion class, protected motion class. If it has this in it, you can only access the variable using the this keyword. If there was something else that is of the same class, and you try to access its private this members, you couldn't, because you wouldn't be using the this keyword to access. I mean, you should be familiar with the this keyword from from Java or C++ or Programming 1, where the this keyword is like a pointer or a reference that belongs within an instance of a class. It is the pointer that the instance of the class uses to refer to itself. So private this is like the most restrictive. Private motion, when you're inside of class motion, means we can access. It doesn't have to. We can access anything that is in class motion, type motion can access it. It doesn't have to be with the this keyword. So for example, if we pass in another instance that is of type motion, we can access its private motion values from our motion object, because we're not using the this keyword, but they're both in the same class. Protected is the same as private, but it includes subclasses. So for example, protected this means that subclasses of motion can also access it as long as they're using this keyword. Protected motion means subclasses motion can access it. They don't need to use the this keyword. And we just have a immutable value, a variable that's incremented every time we call some function. Function return me returns my type, or my type is a type that extends motion. If we have a type that's with a name like my type, it usually refers to the type of the thing itself, the type of the class or whatever. And we have another function return motion that just returns motion. The difference between these is, when you override my type, you're going to override it with a subtype. So this will return something. This can return something more specific than motion, where this will just return motion. So we have an abstract class animal. This is our primary constructor. The primary constructor is what you use to generate instances of that class. Or if it's a superclass, you can inherit from the primary. If you have other constructors, those other constructors will call the primary constructor. In the case of an abstract class or a class, you have to specify val or var in order to create a variable for that abstract class. Whereas if you just have something like, if you just had like a case class, for example, you could leave out val and the variables will still be instantiated. You also have package private and package protected. Something is private to the package, anything in the package can access it. If it's protected, anything that's in the package or the subclass of this can access it. Class person. So we extend animal. If we leave out, if we wanted to, we could specify like false, where it would assign this variable to either false or true. If we leave that out, it'll just use the default value, which is true. This equals here in the constructor will specify your default value. You can print out the variables. We can see that some things work and some things don't. Like if you have something that is package private, that works, public works, protected works. You can have protected with this or private with this. Oh yeah, protected with this work, but private with this won't. So this value is private. The scope of the value is private this, which means that only something that is accessed with this, which we're doing, we're using this, but only with this and inside of the scope of the motion trait. Right now we're inside of person 1, which is a subclass of motion, so private this won't work. But since we're a subclass, protected this will. Does that make sense? So we're using the this keyword. There's motion, there's person 1. If this keyword, if we're inside of motion, we can access private this in motion. If we're in the subclass, we can't access private this, but we can access protected this. We can override my type to give it something more specific. Here we have my class type is person1, and my type is this dot type. The difference in between these two is that person1 is the type of the class. So we have a class of type person1, whereas this dot type is the type of the instance of type person1. So this dot type is a singleton type. This dot type can be used in places that accept person1 because it's more specific than person1, but it can't be used in if something were to only accept this dot type, it would only accept this particular instance because this dot type is the type that is specific to this reference pointer, if that makes any sense. It's a singleton type. So if we say something returns person.this.type, it means it returns something of the type of this instance. So the only thing that it can return is this, because this is the only thing that is person1.this.type. Whereas if you just return anything of type 1, you could return this, or you could return any other object that extends person1. So this is a singleton type, and this is a class type. And the class type is generic for anything that anything that is an instance of person1 accepts the class type, and this only accepts something that is of type this. Person2, we override my type with person2, where my type is anything that extends motion. Return me returns my type, it returns person2. And you see the difference between these two is this, returns motion, and this returns something that is more specific than motion, right? So these two here, return me and return motion, correspond to these two, where this returns more specific, and this returns general. You have a bacteria, extends animal, false. If you want to be more specific, you can actually say, specify the name of the variable. So it was animal, but it actually is multicellular. This is nice. Sometimes if you have a lot of variables being passed, it's really nice to just be specific and say is multicellular equals false. Let me scoot this over a little bit. There we go. If we wanted to sort of click our way through, we could go, press the down arrow, and it should eventually take us to, I can rerun this because I kind of moved stuff around a little bit. Implicit val f. So we have implicit parameters. Implicit parameters allow you to pass the value in the place that is referred to as implicit. So this 5 will get sucked into there because that's the implicit that's in scope. And what's going to end up being printed out here is going to be 5. If we were to go through sort of down arrow, you can press the down arrow and it'll jump to the print statement. So we can jump to this print statement. We can go navigate around. So here we go. So print func, control B. So this is calling this method. If we were to press control Q, we would see that it takes an implicit. If we were to press control shift P and then press enter, we would see that the implicit parameter that's being taken in would be this. And if we wanted to desugar it to see what it compiles into, we can look first at phase 1. So this is just implicit func semicolon. We're like, it doesn't desugar into anything. But look at phase 4. Control F, implicit func. Boom. See this implicit func F here? This F is taken from there and it's put inside. So this, some point in the compilation is transformed into that. Oftentimes, if you're confused, it's really good to take a look at the compilation. Then we have this implicitly int, where implicitly looks for, there's a generic type t. In this case, we assign t as int, and then we're looking for an implicit of type t. So we're looking for an implicit of type int, and then we're going to return something of type t, which is, in this case, is going to be type int. So what does this do? It finds an implicit of type int, and if it doesn't, it won't compile because it can't. The function needs to have a parameter for it to compile. So we look at implicitly int. What happens with implicitly? Scala.this.predef.implicitly int f. So we know that implicitly is also grabbing the f. And if we want to check, we can press Control-Shift-P and then implicitly and enter, and we can see, oh, there's where our implicit variable is coming from. This is just the same thing except with floats. ToFloat is there. You could also have something like, there we go, like double, char, int. But ToFloat is perfectly good. F, enter. One thing I really like about statically typed languages is that you can just press Control Space and then you just get all the documentation and autocomplete, and you don't have to worry about spelling or typing. Just scroll, down arrow, enter. It compiles, don't have to check. Now we're going to do implicit conversions. Let's say we have a final class int wrapper that takes in an int, has a function called sayHi that prints hi. Let's import the implicit conversions feature just to be explicit about what features we're using. Then implicit def int wrapper. Let's say we have a function. Int wrapper takes an I and returns a new int wrapper of type I. This method is an implicit conversion method. The compiler will sort of grab this method and insert it in places where it's needed. So let's say we have val6, which is going to be of type int, right? 6 is of type int. Then we call something like 6.sayHi. The sayHi method doesn't actually natively belong to integers, but you've got this. If you look carefully at the method, you'll see there's a thin gray underscore, thin gray line. That thin gray line means the method is made available through implicit conversion. And if we want to figure out what implicit conversion is going on, we can go to navigate, and then implicit conversions should be there. And then wrap int wrapper, and boom, cool. Let's try that again, right? So Control-Shift-Q, enter, and it's saying that this method is available by applying this implicit conversion. And if we wanted to actually see the implicit conversion happening, we can press Alt-Enter. Oh my god, look, wrap int wrapper 6, and then Control-Shift-Z to undo. And then Alt-Enter. Oops. Alt-Enter. Sorry. But you get the idea, right? So, and then Control-Z. So this and this are the same. All what it's doing is the compiler is going, hey, this method doesn't exist on int, but we can search for this implicit def that takes in an int and returns an int wrapper where int wrapper has sayHi method, and then we go boop, 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 got it. And if we were to go to sayHi and press like Control B, then we would see, oh, sayHi is coming from this class. And then if we were to look into the partial compilation, where we had something like wrap int in wrapper, what's going on here? Case, implicit func, implicit def, implicit float, final class, wrapper and wrapper extends any ref, some accessor, implicit conversions. So if you look here, these two, by phase 4 of the type compilation phase, these two things are the same, right? So this turns into that, and then these two things, end up being the same. If you wanted to, you could also just implicit, you could also just actually get rid of this, get rid of the int wrapper. Oh, sorry, you don't need the int wrapper. You could just say like, there we go, int wrapper 6, or just get rid of that, and you would say 6.say hi. And what would end up happening is if we were to go do our same thing, Control Shift Q, int wrapper, you would see, oh, that's where it's coming from. And having an implicit final class is the same as like an implicit conversion method. It's just less, it's just a little bit less boilerplate. You don't have to worry too much about implicit evidence, but this just says that implicit evidence, some type, is a subtype of tuple L, tuple R, where tuple L and tuple R are just two different types that are in a tuple. If you call only tuples with 1, 1, it compiles because the type here has to be a tuple. If you try to do only tuples with 1 in it, this is not going to compile. It doesn't highlight in red, but it's not. You've got ranges, inclusive range with 2, 1, 2, 10 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Exclusive ranges 1 until 10 is 1, 2, 3, 4, 5, 6, 7, 8, 9. You've got your for loops for I in range 1 to 10. That's the same as like I to inclusive range. If we follow along with the clicky thingies, you can just click there and we'll go to it. You can have loops within loops, or more often what you'll do is you'll end up with something like this, where you have sort of like something like this, right? Where you have, don't worry about it now, but you normally wouldn't do nest like this. I'm going to Google it actually. You could just pull up Scala nested for loops. You would say, you just have like multiple arrows. So instead of, like this, right? For I 1 to 2, j 1 to 2, println ij, just like that. So if you wanted to do your loops, you could do something like that, and this would be the same as sort of nesting. Matrices, break. Okay, we're back. We're going to cover lists with map and flat map. Let's say we have a list of 3 elements. We have a function, 2 ints, that takes in a string and turns it into a list of ints. A string, you can think of it as like almost like a list or a container of characters. I'm actually really curious. No. Anyway, if you were to map each of these strings into a list of integers, you would end up with a list of integers, where you would have 3 lists of integers. So you would have a list of integers. If you did flat map, it would flatten. So instead of having instead of having one list of integers, another list of integers, and another list of integers, it would combine all of that into one list. The difference between map and flat map. Map, you're going to see this a ton, but map, takes in A, returns a B. Flat map takes in an A, returns a container of B. You can think of it as. So map something, let's see, map of A, something that, say you have an F that takes in an A, returns a B. And whereas flat map, you end up with takes an A and take an A and return something like a container of B, where a container is a monad. Hopefully you know what that is. If you don't, take a functional programming tutorial. A good way to learn Scala is by learning Haskell. They're very closely related. But the difference is that you can, we'll see later. But basically, if you just map, oftentimes you're done, whereas flat map allows you to nest. So if we had something like character inside of matrix characters, this arrow means something different than it did before. Before, the arrow meant like, get each element out of a list, or like each element out of a range from 1 to 10. Here it means get each sort of string out of the list of strings. So character is a string in the list of strings. So for each character inside of for each string character inside of matrix characters, then we have, and then inside of that, for each int inside of for each int produced by 2int on that character. So we have three characters. We call 2 ints on each of them. We end up with 3 sort of lists of ints. We yield that int, and what's going to end up happening is we're just going to end up with one big list of. If you look up the result type, Control Q, we end up with one big list of ints. You'll see that this flat map, a flat list 2, what's going to end up happening if we go first to phase 1, the typer. Okay, so look at what happened here. Matrix characters dot flat map, take in a character and return 2int on character, right? So we take the character, we convert that to an int, and then we map that int to itself. So by using flat map, it allows us to sort of do nesting. I'm not going to go into like super detailed functional programming stuff, but basically, if you look at, so we have character, 2int character dot map int to int. So the difference here is by using flat map, we end up with one big list, whereas if we were to change this just to map, which we could actually do because we're not we could instead do map here. What would have ended up happening instead if we did map was, instead of getting a list of int, we would have ended up with, so let's actually pull up both of these. Let's call this 2.1 and 2.2. This is dot flat map, and this is dot map. Oops, yeah, there has to be a type on this. Let's say there's a character of type string, I guess. Something weird is happening. 1 second. Flat list 2, let's go to flat list 2, and flat list, let's call this flat list 22. Oh, oopsies, let's undo the stuff that we did here first. There we go. Sorry. Oh my god. So if we were to just take this stuff, there we go. So everything that's in here in the phase 1 of the compilation will turn into this stuff that's in here, right? So, this gets converted to a flat map, and this gets converted to a map, and then this to this gets converted into sort of that to that. If instead we use flat map, if we use map instead of flat map, we would get a different type up here. So the difference is map. Map is going to produce 3 separate lists, so the type of this is going to end up being list of int, and if we press Control Q, we'll see this list of int. These two are identical. Actually, let's do 3 of these that are identical. 3, 3, and this is 2int underscore. You'll see this underscore notation. Oftentimes, it might confuse you, but matrix characters.flat map, and we have a function that takes in a character. Actually, let's make it even more verbose. It takes in a character of type string. There we go. So we have a function, matrix characters.flat map, takes in a function of type character, which is a string. This is a higher order function, so this function is going to be applied to that list. So it takes in this function of type string and returns character of type string and returns 2 ints on that character. And so this function ends up being applied this function here. Remember that this is the same as that. There we go. This function ends up being applied to this because it's a higher order function. That's the same as we can leave out this colon string, and it's the same as character to 2int character. We can, because this character is repeated twice, it's a form of boilerplate. Scala people don't like boilerplate, so they can just go 2ints whatever, and it'll just fill in the variable name. And if we wanted to get rid of the whatever, we can just boom 2int, and then it'll just apply that function to each element. Oftentimes, the amount of boilerplate that's acceptable depends on how sort of self-documenting you need the code to be. Sometimes, it really makes sense to leave in this variable name because it's some sort of documentation that has to, convey information to the reader. And other times, it doesn't matter. So, but yeah. For example, let's try to if we were to read this outer list, which is list 1, 2, 3 dot flat map each element, and then list 1, 2 dot map inner to inner times the element on the outer. And what we're doing here is by sort of we have this big function, and then we have sort of this inner function. And the inner function here is actually this inner function is actually using variables provided by the outer function. That's called closures. The difference between a closure and like an old-fashioned function is that closures have access to what's outside of their scope, and it allows you to nest them, and the inner closures access what's on the outer. So in this case, this inner closure accesses the element from Control B, jump to declaration, that outer closure. This is a pattern called the monad. You'll see this pattern a lot in functional programming. This is just a var arg. We've seen it before. If we wanted to pass in a bunch of parameters with var arg, we could do that. We could also convert lists to var args using colon underscore star to cast to var arg, colon underscore star cast the list to a var arg. this here, it just means unit. Sometimes, if you want it to infer a unit, you could just sort of leave this out and just provide that, and it'll always infer a unit, even if the last thing is even if the last thing is not unit. If the second to last thing is not unit, if you add this little sort of trailing close braces, it'll infer unit, and that's for people who they want to leave out the return type. Generally, it's better to leave in the return type, just because the return type is, especially for public methods, because it kind of goes along with the Java doc, and oftentimes people will just look at the method signature. There's this thing here, val. So let's say pairs is 1 1 2 2, pairs.forEach. Remember, this is the same as that. So this is like being passed into that. For each pair, we have this equals pair. So this here is tuple decomposition. We're saying that the first element of the pair goes to the first variable, and the second element of the pair goes to the second variable. So the first variable is going to be a string. The second variable is going to be control Q. We'll see. It's going to infer an int, right? Obviously, because of the proximity, it should be clear. You shouldn't need to put it in explicitly, but oftentimes when you're starting out, it helps to have the types there. Println that. We've got, we can import the annotation for tail recursion. And what this does is it checks to make sure that tail recursion optimization is happening. If we go to tail recursive count in the parser phase of the compilation, we should see that this while loop is actually converted into like a, so if we were to go to back here, okay, so we have our if and our else. If I equals 0, 0, else, done. So we have that, and then we have that, else. So there's no while loop optimization happening in this phase. If we go to the typer phase, still no while loop optimization happening. But there is a phase where while loop optimization does happen, and it is in the tail calls phase. Right? So in the tails calls phase, phase 11, if we were to go to tail recursive count, so we're saying if I is equal to 0, print done, returns 0, else tail recursive count main. So then we're calling here I minus 1 as an instance of int. That's weird. Let's see, tail recursive count. Oh, I see what's going on. So this tail recursive count up top, this is the method declaration. And this one down here is like your, go-to counter, where this is like a counter, right? So you're saying here, this here is like kind of go to here, or go to, wait. Main.this, I minus 1 as an instance of int, and tail recursive count 2. And I don't really understand the bytecode that well. But eventually, at a certain point, this gets optimized away, so that eventually it's going to just be else tail recursive, this main. Eventually, it's just going to be, go-to statement, go-to statement. Oh, I see. So this is a go-to statement to that, and we're just going to, from here, we're going to go to here, and then here, I minus 1, go to here, here, I minus 1, go to here, and then we finish off with that. So, yeah. This basically optimizes in the recursion into like gotos. We've got lazy variables. What happens with lazy values is that uh-oh, is this compiling? Oops. There we go. What ends up happening, so we did that, we did this. So we're on lazies. Okay, so we have a lazy value. So we've got this scope, and we're assigning it to this value. Lazy values, this code will only be executed the first time the lazy value is read. So we're on, what line? Here. So if we go to there. So the first time the lazy value is read is here at my lazy. When this happens, what ends up occurring is it should print out, let's get lazy. There we go. So at this point in the program is the first time that my lazy is read. So it's going to print out let's get lazy with 3 lines of stack trace, and then it's going to do this tail recursive count with 2. But if we look at let's get lazy, first line of stack trace, second line is let's get lazy, third line is there, right? So this boom, 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 this triggers the call to, what the, something is up. Oops, I accidentally moved that over. All right, but anyway, this triggers the call to that. But then the next time you do it, the next time you call my lazy, it doesn't trigger this code again, because this, the first time you read, everything gets executed. The second time you read, it'll just return the last value, whatever is cached. In this case, tail recursive count is going to return 0, because if you go Control B, it'll just keep decrementing until 0. So lazy values will, you assign this chunk of code to the value. The first time the code is read, the code is executed and the value is cached, and then every subsequent time it's read, the cached value is provided. Whereas if we just assign with a regular value, if we were to just do this, what would end up happening is this would be executed immediately. It wouldn't defer until the first read, whereas this defers execution until the first read and then caches. We've got different types of function decomposition. So let's say we have this function that doesn't take in any parameters and it returns an integer. Oh, by the way, the difference in between with parentheses and without parentheses is with parentheses means side effects. You know, it can do I/O, it can print out something. No parentheses means no side effects. That's the way it's supposed to be done. If I made a mistake and didn't do it that way, I just messed up. But this underscore after the function will convert this function into a value of type that takes in nothing and returns an int. This would be the same thing as if we said, you know, value return 5 func val of type, you know, function that returns an int equals, you know, takes in nothing and returns 5. Yeah. So if we just look at this, these two look the same, but this is a function, and this is a value. It's possible to turn functions into values using the ETA decomposition, eta decomposition. If you look at the type on this type here, is the same as this type after the decomposition of the def. But if you were to just assign it like as is, what would end up happening was if you press Control Q, you'll see that this is an integer. Why? Because it's just executing the function and returning 5. It's not, right? val5 value type int equals return 5 func. What this does is it'll execute return 5 func, return 5, and then assign that 5 to there. And then when you print this at 318, what you're going to end up getting is you're going to end up printing what's going on? There. Oh, there we go. You're going to end up printing 5. So this is going to end up prints 5. And if you did 5 val plus pause, doesn't matter. A little bit about currying real quickly. Currying is when you can pass in one parameter, you get back a value, and then that value you can pass in another parameter, and then you get your final result instead of having to pass in both parameters at the beginning of the function call. So for example, if you had, so here's an add function with no currying. Here's an add function with no currying, but it's a value. Here's an add function with currying. So you'd say like val add 5 to this equals currying addition function 5. You could do val 6 equals add 5 to this 1. Val 7 equals add 5 to this 2. Val 8 equals add 5 to this 3, so on and so on, right? Because you're reusing this function where you only did partial application of the parameters. You can also do, so A to decomposition, this turns it into a value. And then after you turn it into a value, you can do dot curried, and that turns it into a curried value. So if you've ever seen Haskell, this is what Haskell style function declarations look like. So you could do the same thing that we did there, but with add currying value. So add 5 to, we end up with a function that takes in an int and returns an int. And then 6 add 5 to 1 is just an int. When I first saw these sort of type signatures, I found them confusing. The way you should read them is left to right. So if we were to think of this as sort of having its own set of parentheses around it, we have something where we have this, we pass in an int, in this case 5, which is of type int, and we return something of type, takes in an int and then returns an int. And then we pass in 1, which is of type int, and it returns something of type int. So that's the way you should think of those type signatures. Null is evil. Don't use it. Instead, use options. If you do sum of null, this just becomes none. You can almost guarantee it. Wait, Jesus. Sorry, I forget what the. So if we look at, oopsies, extends option. If you look at none. Alright, that's not working. Anyway, if you just Google something like Scala sum none, this guy's really good. I highly recommend him. Let's see. There, it's just none, no parentheses. So if we just had none, what these are is this is used instead of null, and what you'll end up with is something of type. You could actually cast it into something like option int and option int, and then for value inside of some val1 println value. And the nice thing about some none notation is that the if null don't do anything check is built into it. So what this says is for some value, you extract the value inside of it to get value, which in this case is 1, and then we print 1. But if it was none, we try to extract the value, there's nothing in it, we skip this entirely. So we can leave out the explicit, this as opposed to like, if some val2 is equal to none, or, is equal to null, don't do anything else, println some val2. This does something similar to that, but it's a lot more concise and clean, especially when you start to nest. But yeah, null is evil, don't use it. Any's at the top of the hierarchy, nothing's at the bottom. All references extend any ref, all values extend any val. Pause. Okay, pattern matching. Let's say we have a list that contains tuples where the first element is a string and the second element is also a string. If you wanted, so these are the same. If you wanted to cast it to something, we could do that, but it doesn't because string doesn't conform, the cast won't work. But here we just have string string. We're saying for each tuple in Lang's tuple match, and we're going to do pattern matching. So in case the first pattern works, Scala and whatever. So in case we have Scala and then whatever, this means automatic match, println Scala pause. And in case, Lang author, so just two variables, println Lang and author. So here the underscore is used for like a doesn't matter variable. We could also have written in doesn't matter, and we would get the same effect. But I'm going to leave in the underscore just because it looks better. At first it annoyed me, but it just from an aesthetic perspective. So if we were to actually run this tuple, we would first print out, I ended up writing stuff, but the first thing that prints out is strustrup, which is going to be the first thing here. So let's look at the execution of the code. So the first line is this. We go here, case Scala underscore, it's not a match. Then we look at the second line, Lang author. It is a match, so we print ln C++ strustrup, which if we look here, C++ strustrup, that's a match. Then we look at the next line, Scala or Dersky. We go Scala doesn't matter. What do we print out? Scala. Okay, cool, so the patterns match up. See, boilerplate function. Okay, so we're going to cover partial functions really quickly. Partial function, a partial function that takes in any and returns a string. All right, we have is defined at, which says where is this partial function defined, and then we have these cases, string double, and then return whatever the case is. So in this case, it's covered for any, which if it's an instance of string or if it's an instance of double, return true, else return false, and then we have it covered for these two cases. And in any other case, if we try to do something with it, it'll throw a matched undefined error or whatever. And then we have another partial function, which if we had something that's a little bit, so if we were to try 77, boilerplate function that is defined at 5 versus, well, let's look, right? 5 is an int. Is it defined at int? No. So we're going to end up with false. And then boilerplate function dot apply 5 plus pause. It's going to say is not defined. So I'm going to rerun it. But then let's say we have another partial function, also of type any string, but this one, we're not going to have all the boilerplate. We're just going to say any case, call it neither string nor double. We can compose these partial functions together. So boilerplate function or else partial function. So this covers anything. This covers string and double. So this whole function will cover string, double, and anything, which is anything. If you combine two partial functions, you still get a partial function, but in this case, it's not really a partial function because it covers any input, so it becomes a whole function. In mathematics, a partial function is a function that doesn't accept any input. It only accepts a certain subset of the input. Oops, 6 is already defined. Whole function, implicitly printable. Don't worry about that. Oh, there are seal traits. Those work with case classes. Seal trait is a trait where all of its subclasses have to be in the same file. It's convenient to do it this way because pattern matching works better because you can guarantee that you've got one sort of pattern matching case for each subclass. Case classes like classes, but they've got class class foo, x of type int. You don't have to explicitly write in val or var. It's just automatically val. And it comes with some built-in methods like they come in with some built-in methods, such as most commonly used built-in method is .copy. It's not working right now, but there we go. Copy equals. So you've got a nice copy, and you can copy it and change one of the variables. It'll only copy the variables that are inside of that case class. If you wanted to change it up, you would actually have to override the copy method. X of type int equals this dot whatever. If you wanted to let's change it. Let's see, call this x2 of type int equals x. This is being weird. Override def copy equals copy method copy overrides nothing. Don't worry about it now. But yeah, this is the most commonly used thing. If you want to make it copy stuff from like the superclass or some other class that's inside of it, you're going to have to override copy, because copy just copies what is inside of it. But it's a lot better than clonable. My class, return me. We've got type constructors. We've talked about these. So if we have a type constructor list, and we type constructor list, int, boom, we get list of int. Got singleton types. We talked about these. Path dependent types was in a different episode. Whew. I think that's most of the things. I think that if you can sort of correspond the stuff in the processed source code with the stuff in the actual source code, and if you can understand the output of the typer, this is really hard to read just because there's so much like sort of wraparound. But if you could actually go through understanding Scala, source, compilation, and you could actually sort of read what your code compiles into. And if you wanted to, you could actually even compile. So if you looked here, it says -xprint typer, and if you ran it, you get all this stuff. All of this stuff here. So all of this stuff here is the same as what's in here. So this here, right here, is the same as what comes out there when you do sbt run, when you run it. And the reason is because I'm running it with this xprint typer command line option. But xprint typer isn't the only command line option that you can use. You could use xprint parser, xprint namer, xprint patch, xprint patmat, right? And so you want to use these to sort of compile your source code into something that's intermediate, that doesn't have so much syntactic sugar, so you can understand what your code is doing. And I think that if you can understand sort of the intermediate code and you can understand your code, it's like, okay, the language finally makes sense. Thank you.